Hi, chemistry friends. We are going to be taking a look at Unit 1, Atomic Structure and Properties, Topic 5, Atomic Structure and Electron Configuration. So you have done some review from Honors Chem with electron configuration and some review on some basic atomic structure. We're going to take that and add to it the new topics that apply for our class. So we're going to investigate the electronic structure of atoms in order to explain why elements have a unique emission spectra. So that's going to be something we're building towards in this section for our unit. All right, so looking at atomic structure, quick review. An atom is made of 3 subatomic particles, so particles that are below the level of the atom or make up the atom. We have protons that are positive and have a relative mass of 1. They're in the nucleus. Neutrons are neutral and have a relative mass of 1 and are in the nucleus. And electrons are negative and have a relative mass of 0, and they're in orbitals surrounding the nucleus. So we have our protons and neutrons in the middle. That's where most of our mass lives. And then the electrons are in the orbitals, SPDF, outside the nucleus. Atoms are identified by their number of protons in the nucleus. Changing this number changes the element. So going across our periodic table, element 1 is hydrogen, it has 1 proton. Element 2 is helium, it has 2 protons, and so on. Atoms of one element with different numbers of neutrons are called isotopes. They have different masses, but the same number of protons. So the atom is the same, the element is the same, except for the number of neutrons. So when that changes, they change the mass of the atom, but still the same identity. They're typically also a neutral charge. So usually when you're changing isotopes, you're still looking at the same number of protons and electrons. Atoms of one element can also gain or lose electrons, making them ions. This causes a change in their overall charge. Gaining electrons makes the atom negative, while losing electrons makes it positive. We have to keep that straight. When you gain electrons, you're gaining negative particles, so you become more negative. If you give away electrons, you're giving away negative, you become more positive. All right, talking more about electrons. The electrons in an atom are arranged in orbitals within energy levels. So the orbitals are the s, p, d, and f shapes. The energy levels are the rings around our Bohr model, or the different areas where we find electrons. So we can make some connections between our electron configuration and this Bohr model. So first we can see that the first number, the 1, s2, so that's the first energy level. The electrons are in the s orbital, and there's 2 of them. So in our first energy level here, we have, so our first energy level would be this one, that's energy level 1. We have 2 electrons, 2 of the red dots in that one. Okay, and those would be in an s orbital. In the second energy level, we can count them up. We have 2, 4, 6, 8. So those are the 2s and the 2p6 electrons. So 6 and 2 gives us 8 electrons. So that's in the second energy level. Then we have the third energy level and fourth. So our third energy level, we have 2 electrons in the s orbital, 6 in the p orbital, and 10 in the d orbital. Okay. Just because we added the 3d electrons last does not make them valence electrons. We have to pay attention to what energy level they're in. Those are in the third energy level. So our d orbital is kind of funky because we add electrons in our s orbital, the valence electrons, for 4s, and then we go back to the inside. And it happens because it's more stable for the atom that way. So our 4s electrons are our valence electrons, these 2 up here at the top. So core electrons are the ones in red. Those are on the inside energy levels, core electrons. And then we have valence electrons, those are on the outside energy level. Okay, so we have core versus valence, and we'll refer to them that way a lot of the time. The other thing we can connect this to is our periodic table. As you have seen with electron configuration, the first energy level is row 1, second energy level is row 2, 3, and 4 going down the left side of our periodic table. This is my rough sketch, right? So going down the left side, we can number the rows, and those are the periods. They're also the energy level numbers. Then we've got the different sections. The first two columns are the s orbital, the right side is our p orbital, and the center is the d orbital where we start adding those electrons. There is going to be a separate video looking at the f orbital available to you guys as well later. So now we're going to look at the electron configuration of ions. So when we deal with ions, we're dealing with a change in charge. So ions are formed from the removal of electrons, making them positive, or the addition of electrons, making it negative. The electron configuration of an ion can be written by first starting with the ground state electron configuration, or the normal electron configuration of the atom, and then adding or removing electrons to form the proper orbitals that create the right charge. Okay. So if we have a negative ion, or also called anions, they have electrons added to increase the negative charge. So we're trying to create negative ions, we have to add more negative stuff as to gain electrons. So for example, here's the regular electron configuration of phosphorus. When it creates an ion, phosphorus adds electrons to fill the p orbital. Phosphorus gets a charge of 3 minus, or -3. And it does that, we've seen the pattern on the periodic table, so that group that phosphorus is in always gains 3 electrons. It's group 15. So they become a 3 minus charge. So how would its electron configuration look? Well, we would write P3 minus, so we write it with its charge, and then we are going to change part of the electron configuration, okay? So 1s2, 2s2, 2p6, that all stays the same, 3s2 stays the same, but we're trying to add 3 more electrons. We're going to do that by filling up the p orbital that was already there. A p orbital can fill up to 6 electrons, so this is going to become 3p6. All right, we add 3 electrons to the 3 we already had, and we get 6 electrons. So this is the proper electron configuration for P3 minus. So if you see a charge on something that's asking for an electron configuration, we have to take that into account and adjust the number of electrons for it. If we're dealing with a positive ion or cation have electrons removed to decrease the negative charge. Okay, we want to decrease how much negative is or make it more positive. So let's look at another example. Aluminum. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. When aluminum creates an ion, it loses its valence electrons, and aluminum gets a 3+ charge. And now the video is covering that up. So it gets a 3+ charge. Aluminum wants to get rid of its valence electrons and get a 3+ charge. So we are going to take the aluminum electron configuration, and we're going to remove 3 valence electrons. We start from the highest energy level, which is 3, and we start with our p orbital. We're going to take those electrons out, that's 1, and we're going to take the 2 s electrons out, and that gives us a total of 3 electrons removed. So this would be our final electron configuration for aluminum. All right? All right, now we're going to take a look at electron configuration of transition metal ions. So transition metals become positive ions just like other metals. So most of our periodic table from the stair-step line on the right side all the way to the left are metals except for hydrogen. So in all of those metals become positive ions. So an example would be zinc. We have its electron configuration listed there, and when it creates an ion, it loses its valence electrons, and zinc gets a 2+, little typo there, 2+ charge. We will review later how we know what the charge is for transition metals and how we can figure those out. We'll get to that again. When transition metals lose their electrons, they lose their valence electrons first, just like other metals, but we have to be careful when we're writing their electron configuration. The valence electrons are the highest energy level, not necessarily the electrons at the end of the electron configuration. So we really have to be careful about which electrons we're removing. So if we took zinc 2+, if we look at its regular electron configuration, its highest energy level is 4. And it needs to lose 2 electrons to get a 2+ charge. So we're going to take out those 4s electrons. And our electron configuration becomes what we see here on the right. So it goes 3s2, 3p6, 3d10 at the end of it, because those are all on that third ring, that third energy level. We lose the outside ones on that fourth energy level. So let's try a couple of elements. Try a couple more. We're going to try first tin 4+, SN4+. So this electron configuration, if we can go ahead and do the shorthand version. So tin is in the 5th energy level. So the noble gas in the previous energy level would be krypton, Kr, and we can put that in parentheses. And then we can add what would be next. So we're going to go ahead and do tin's regular electron configuration, and then we'll see what we remove to make it an ion. So it is going to be, looking at my periodic table, we're going to have 5s2, 4d10, because it fills up the d orbital, and then tin is the last one, or is in the p orbital, and it's the second element in that p orbital section. So 5s2, 4d10, 5p2. So if we want to make its ion form, so this would be for just tin, Sn. If we want to make it tin 4+, we've got to remove some electrons. So we have to remove the valence electrons first. So our first valence electrons we want to remove are these 5p2. Those are on the highest energy level, because they begin with the 5. We're not going to take any from that 4d, and then we'll take these 5s2 electrons. So 2 from the p, 2 from the s, and that's our 4 valence electrons. So this would become krypton 4d10 to properly write its electron configuration of the ion. All right, let's try one more. We'll try chromium. If you want to pause and maybe try chromium out by yourself, that would be a good idea to practice. So let's try it out though. So chromium, do the same thing with the shorthand. Chromium is in period 4. So the previous noble gas is going to be argon in period 3. Then we're going to do 4s2, and chromium is in the 3d section, and it is 1, 2, 3, 4, the 4th element over. All right, if we want to make it chromium 3+, we have to remove 3 electrons from it. So first, we're going to take the valence electrons. Those would be these 4s electrons because it has a higher energy level. We're going to take those away. That only gives us 2 valence electrons though. So now that we have no more valence electrons, this is when we are allowed to take electrons from that d orbital. Okay? So chromium 3+, we can take 1 electron from that d orbital and reduce it down. So we would end up with Ar 3d3 for chromium 3+. That would be its electron configuration. So it would have all the electrons the same as argon, and then we take away the 4s2 and drop the 3d back down to 3. Okay, so that's how we do electron configuration of transition metal ions. So we're now going to take a look at paired versus unpaired valence electrons. Valence electrons occupy their orbitals and suborbitals in pairs. Although they are of the same charge, which is negative, they can be in the same space because they spin in opposite directions. So even though they're both negative, the electrons can occupy the same area or space in those orbitals because they spin opposite of each other. Which is kind of interesting. So we often can show electron configuration represented in orbital diagrams. This is something In my classes, we typically introduce an honors chemistry and draw these diagrams to help us determine electron configuration. Okay, so on the left we have two forms of oxygen. So both of these are oxygen's orbital diagram, okay, for O. So it has the 1s2 electrons, the 2s2 electrons, and the 2p4. So 1s2, 2s2, 2p4 for the electron configuration. You'll notice that the way the p orbital is filled, so we fill up the 1s orbital, we've got the 2 electrons with their arrows representing the 2 spins. The 2s orbital is full, and when we get to the p orbital, we separate the 3 electrons and then we start pairing them. So these are both representations of that. Sometimes they just use a line underneath, sometimes they use a little box. Another representation over here is of iron. This one's kind of interesting because it doesn't just show the orbitals, it also shows their relative energy. So as they increase in energy, they get further from the nucleus, and we can see how they are kind of spread out. So this also shows us that the way that they fill up the orbitals is based on the energy that they have. So those are some representations of our orbital diagrams. So with these diagrams, you'll notice that when an orbital is filled, all the electrons are paired up. So we can see over on the right here with iron, we got this 1s orbital, it's full. We've got our 2p orbital over here, it's full. All the electrons are paired up, etc. Now, we do have unpaired electrons in something like this 3d orbital or our 2p orbital down here in oxygen. Since unpaired electrons give opportunities for bonding, you may be asked how many unpaired electrons an atom has. So we're going to take a look at these ones. Oxygen and hydrogen. The unpaired electrons may be in the sp or d orbital. They could also be in an f orbital, but we don't see that on the test really. So if we look at oxygen down here, oxygen's 2p orbital has 2 unpaired electrons, right? 2 spaces where more electrons could fill in and bond with an oxygen atom. Iron over here in its 3d orbital has 1, 2, 3, 4 unpaired electrons. So those can give opportunities either because it's iron and it's a metal, it would want to give up valence electrons. So that could happen with iron. So it helps us see how these different atoms can interact with each other by gaining or losing electrons. Now, we can use the periodic table to help us determine how many unpaired electrons an atom has based on its location and the pattern in which atoms fill their orbitals. So we're going to take a look at that pattern and how we can predict how many unpaired electrons something has. So here's our paired versus unpaired electrons. So if we look at our diagram down here, our orbital diagrams, this is a list of hydrogen all the way to calcium. So our first 20 elements on our periodic table. So this can help us discover what the pattern is. So we're going to take it just one column at a time, right? Or one element at a time, actually. So hydrogen has 1 unpaired electron. I'm just going to fill in over this periodic table how many unpaired electrons each element has. Heliums are paired, so it has 0. Then we go to lithium. I'm going to continue down the list. Its 1s orbital is full. Its 2s orbital has a 1 unpaired electron. Beryllium has no unpaired electrons, okay, because both of its 1s and 2s are full. Continuing on the right side, number 5 with boron, it has its 1s and 2s full, but its 2p orbital has 1 single electron and it's unpaired. Carbon, we can see, has 2 unpaired electrons. Nitrogen has 3. Oxygen now, when we look at oxygen, it only has 2 unpaired electrons because when it got its 4th electron in that p orbital, it paired up with one of the ones that was already there. Okay. Then when we go to fluorine, we only have 1 unpaired electron. And then neon has none. All right, so we kind of have an interesting thing happening here. We fill up the orbital. Our p orbital has 3 different shapes to it. So we fill them up one at a time. So we gain unpaired electrons. Then we start losing them as we pair them up, going from left to right. So let's keep going. Sodium has 1 unpaired electron, that 3s orbital. Magnesium doesn't have any. Aluminum has 1. Silicon has 2. Phosphorus has 3. Sulfur only is down to 2 because one of the because the other one got paired. Chlorine has just 1, and argon, our noble gas, has 0. Okay, so you might start to see a pattern here, right? When we look at our s orbital, if something is in the s orbital, so that's the first 2 columns, if it's in the first column, that very first column there, are alkali metals, they're always going to have 1 unpaired electron because they're always going to have 1 electron in that s orbital. Everything in column 2 is not going to have any unpaired electrons because the s orbital is full. When we're looking at our p orbital, it builds and then reduces. So we go 1, 2, 3, 2, 1, 0. And we can think of it just like our p orbital here. If I wanted to do like selenium, I would go, okay, it's the 4th element in that p orbital. So 1, 2, 3, 4. So I have 2 unpaired electrons. So it's an easy way to find that. If we wanted to do the d orbital, we could also do that. It's going to start with 1, right? We've got 5. Let me do some erasing here so we can see our stuff. So our d orbital has 5 boxes to it, 5 different shapes to the d orbital. So when we add 1, we'd have 1 unpaired electron. We'd have 2 here, 3, 4, and 5, right, as we fill that up. Then we're going to start to reduce it down as we start to pair them. So 4, 3, 2, 1, and then 0 when we get to zinc. So that's another way. We're going to build from 1 until we get to that halfway point, and then we start pairing them and we reduce it down to 0. So that works for all of our orbitals. So if we're asked, I've seen this in multiple choice questions in the AP exam, just how many unpaired electrons are there in, or they might ask which atom has 2 unpaired electrons or something like that. So we would use our periodic table to help us answer that. So to kind of go over this section, we looked at a brief overview of our atomic structure, just reviewing that. Looked at our electron configuration for ions. So when we have positive ions, they're going to lose valence electrons. When we have negative ions, they're going to gain them until they fill up their orbital, typically their p orbital. And then when we have transition metals in that middle section of our periodic table, that d orbital section, we have to make sure we're taking the valence electrons off of the highest energy level first when they become positive, and then taking them out of the d orbital if we need to. And then lastly, looking at unpaired and paired electrons so that we can answer questions about our atoms based, again, around their electron configuration. So if you guys have questions, make sure you ask me in class and we can clarify any of this. Thanks.